Okay, so let's now solve this problem 15.6. In an engine, we have 0.25 moles. Okay, I'm going to write down as we are getting information. So 0.25 moles. And it's an ideal monatomic gas, so PV equals nRT, or U equals to 3/2 nRT. All these things work here. No? And this gas will expand rapidly adiabatically. Okay, so immediately we know Q is 0 from this information. Okay, and it's the gas that is expanding by itself. So this is work. This work of the expansion is done by the system. Okay, in the process, since we have this very fast expansion, the temperature of the gas drops. So it starts, we call this the initial 1150 Kelvin, and it ends up in 400 Kelvin. And so why does it drop? Because it's a fast expansion, so we are losing energy, and we are not recovering it through heat. So we have this temperature drop. And the question now is, what is the work? Well, how are we going to compute the work? Well, I don't know about pressure, volume. They didn't give us that kind of information, but they tell us about the temperature. And we know that in adiabatic process, there is no exchange of heat. So we know that for the first law, delta U is equal to minus the work. And so from here, we can get what the work is. Well, so what are we going to put for the delta U? 3 halves, N, we have N is 0.25, R is the universal constant. You have that in chapter 13. So you can use this R here. Joule, mole, and Kelvin, and the temperature is given in Kelvin. Okay, so here we put the change in temperature, the final minus the initial. So here you'll see we are going to get a negative value, and so we'll know what is the amount of work that is done. Now, done by the system, 2,300 joules. All right, so this is the first problem. Let's go now for the next problem, the 15.7. What we have now in this problem, let's read it together. We have determine the change in internal energy. Okay, so they want delta U. Okay, so let me give space here to tell you which problem we are solving now. This 15.7. Okay, and the question of the problem is, what is the delta U? The change in internal energy of 1 liter of water. 1 liter of water, we know the mass is 1 kilogram. Okay, initially it's at 100 Celsius and it's going to stay there. It's right at the point where it can boil, and that's exactly what is going to happen. This liquid will boil, will transform into gas. As it goes into gas, we go from 1 liter to 1671 liters. So we go from 1 liter, this is our initial volume, and we end up with an enormous amount, 16 and 71 liters. So this is an incredible change in the volume, and this is what we really use, this big change that we get when the liquid becomes gas. So that's what we use to get work done. That's the whole idea of heat engines. We get big expansions here. That expansions that can be used to move a piston, to make a train move, for example. We'll discuss heat engines later. Anyway, let's come back to this problem. So we have this enormous change in volume. And all this process is done at atmospheric pressure. So we also know that this pressure is 1 atm, atmospheric pressure, so 1.01 10 to 5 in the international system, Newton per meter square. All right. the problem also gives us that conversion from liter to cubic meters, right? So careful here. Now it's 10 to minus 3 cubic meters. There is a 3 that is missing here in these meters. All right. So how do we get this change in internal energy? Well, look, careful here. There is no change in temperature. The temperature is constant. All that is happening in this problem is a change in phase from liquid to gas. And you may say, okay, but then how do we have change in internal energy if we don't have a change in temperature? Well, that equation that we discussed before, let me write it here, the 3/2 of nR delta T. This equation is true only for ideal gases. So it's not true for us here. We don't have an ideal gas. We have a liquid that is changing phase. Okay, so that's not the kind of equation that we are going to use. That is not valid at this point. Okay, so here, even though the temperature is constant, we are changing the internal energy because we are changing the phase of this substance. Okay, so how are we going to get this delta U? Well, the first law of thermodynamics, that is still valid. And that is a law that it's a law, no? So it applies to any kind of substance. It doesn't matter if it's solid, liquid, gas, ideal gas, or non-ideal gas. Okay, so that equation, the delta U equals to Q minus the work, that is still valid. So this is the equation that we are going to use to try to find our delta U. Okay? Okay, so what we need Q. Q is the energy being injected into the system that allows it to change phase. No? And that's the only thing. The temperature is not changing. So the only Q that we have here is mL for latent heat, right? So M is 1 kilogram. So let's put it here. M is 1 kilogram. And the latent heat is given to us here already in the proper unit, joule per kilogram. So we just have to copy this value here, 22.6 10 to 5. So it's a very large value. Okay? Okay, now let's go for the work. Why we are putting minus work here? Because this is work done by the system. The system itself, as it changes phase, it will expand. Okay, so that's why we put the minus sign. And now, what is going to be this work? Well, work is done at atmospheric pressure, constant pressure, so we know the equation here also is P multiplied by delta V. All right, which P, which pressure? The atmospheric pressure that we talked about. Now we have the value here. Which change in volume? Well, here we have the change in volume. But careful about the units again, right? Put this, instead of liter, put it in cubic meters, okay? If you put all this there, you're going to find this final answer, 20.8 10 to 5 joule. All right, so again, I repeat, that story of using delta U equals to 3/2 nR delta T is true only for ideal gases. But the law, the first law of thermodynamics is true for any kind of material, any kind of substance. That is always true. The 3/2 of nR delta T only for ideal gas. And in this problem, 15-7, we do not have an ideal gas. Very well.